Welcome to a new lecture of Advanced Geospatial AI. Deep Learning for Satellite Imaging Analysis. I am Dr. Azad Asub, and today we are validating deep learning predictions against ground truth data, focusing on biomass estimation. We will validate biomass predictions from satellite-derived features in Colab by the individual compute enhanced accuracy metrics like MAE, RMSE, and R-square. Why validate with a ground truth? Validating predictions against ground truth, such as field measured biomass data, is critical in geospatial AI. Why does this matter? First, accuracy assessment ensures predictions, for example, above ground biomass in kilogram, align with the real world measurements. Second, reliability. Metrics like MAE, RMSE, and R square quantify model performance for applications like carbon stock estimation. Third, decision making. Validate models build trust for stakeholders, supporting high performance goals. Ground truth data, like the Excel that we use, provides a benchmark for geospatial predictions derived from satellite imagery. Validation techniques to validate biomass predictions: acquire ground truth, use datasets like we are use, Excel biomass data or field surveys aligned with the satellite resolution. Second, compare predictions. Match model outputs with the ground truth biomass values. Third, compute metrics. Calculate MAE, mean error, RMSE, root mean squared error, MAPE, mean absolute percentage error, and R square to evaluate performance. In today's demo, we will train a neural network on the biomass dataset with the synthetic satellite features, NDVI, and elevation, generate predictions, and validate them against ground truth biomass, mimicking real-world geospatial validation. We will use TensorFlow and Scikit-learn in Google Colab with the GPU support. The demo trains a feed-forward neural network on the biomass datasets, 563 samples, incorporates synthetic satellite features, and validates predictions. Let's dive into a demo in Google Colab to train a neural network, predict biomass, and validate against ground truth data. Open the Jupyter notebook from the course resources. Ensure GPU is enabled and follow along. In runtime, select GPU. This is the script. Import necessary libraries. We are using pandas for data handling, NumPy for numerical operations, and Scikit-learn for data splitting and metrics. TensorFlow Keras builds our neural network and Matplotlib creates visualizations. These are the tools we will use to predict biomass from our dataset. So let's get them ready. Load and preprocess the Excel data. Click on Files, upload to session storage, select CSV file and open. Now let's load our biomass dataset. We are reading the Elizano ITC data.csv, which contains field measurements like tree height and biomass. The dropna function removes any rows with missing values to ensure clean data. Let's print the dataset shape and a preview of the first few rows to confirm everything loaded correctly. Then feature engineering and synthetic satellite data. We will enhance our dataset with a feature engineering. We create a biomass height ratio by dividing biomass by height, which can help the model learn relationships. Since we don't have real satellite data yet, we will simulate NDVI and elevation using random values between 0.2 to zero point 0.8 and 100 to 1000 meters for elevation. The random set ensures reproducibility, features, and target. Now let's define our features and target. The features list includes height, diameter, NDVI, elevation, and our new ratio. This will help predict biomass. We assign them to X and set the target Y as the actual biomass in kilograms. This setup is the foundation for our machine learning model. Scale the features. To improve model performance, we need to scale our features using standard scaler. We transform the data to have a mean of 0 and a standard deviation of 1. This helps the neural network converge faster. Let's apply this transformation and move to the next step. Split the data. Trying to split our data, we use train test split to create training, testing, and validation sets. We allocate 50% for testing and further split the training set to get a 15% validation portion from the remaining 85%. The random state ensures consistency. Let's prepare our model with this data. Next, build and compile the deep learning model. Here's where we build our neural network. We use a sequential model with an input layer matching our feature count, followed by three hidden layers with a 64, 32, and 16 neurons using railroad activation. The output layer has one neuron for our regression task, predicting biomass. We compile it with the Adam optimizer, MSE loss, and MAE as a metric. This is our prediction engine. Then train the model with a early stopping. Let's train the model. We set up early stopping to halt if validation loss doesn't improve for 10 epochs. Restoring the best weights. We feed the model for up to 50 epochs with a batch size of 16 using our training and validation data. Watch the output for loss values. Decreasing this shows our model learning. Next step, evaluate the model and compute additional metrics. Then print metrics. Now let's evaluate. We compute the test loss and MAE, then predict on the test set. We calculate MSE, RMSE, MAPE, and R square to assess performance. MAE shows the average error. RMSE emphasizes larger errors. MAPE gives a percentage error. And R square measures explained variance. Visualize predictions. Let's visualize the results. This scatter plot compares actual versus predicted biomass. The blue points show our predictions, and the red dashed line is the perfect prediction line. If the points cluster near this line, our model is doing well. I look at the plot as it appears. Plot training history. Next, let's see how the model learned over time. This plot shows training and validation loss across epochs. A decreasing trend indicates good learning. If validation loss flattens, early stopping kicked in. Check this graph for insight. The final step, residual plot for deeper analysis. Finally, let's dive deeper with a residual plot. This shows the difference between predicted and actual values against predictions. The red line at zero helps us spot bias. If residuals scatter randomly around it, our errors are consistent. This is a powerful tool for refining our model. Take a close look. Now, let's run the code. Executing. Using GPU in Google Colab helped us to run the code in just a seconds. Velocimetrics, actual biomass and predicted biomass, model loss over epochs, and residual plot. In this demo, we trained a neural network to predict biomass, validated it against ground truth with a test MAE of 61.77 kilogram, indicating an average error of about 6 to 18% of the biomass range. The RMSE highlights larger errors, while the answer of 4.98 shows an excellent fit. The scatter plot shows predictions clustering near the diagonal. The loss plot demonstrates covariance from 0.59 to 4,296. And the residual plot helps identify error patterns such as potential bias at higher biomass values. With the real satellite data, for example, Sentinel-2 NDVI, these metrics, especially MAPE, could improve. In summary, today we learn to validate biomass predictions against ground truth data for geospatial tasks using enhanced metrics like MAE, RMSE, MAPE, and R-square. You run a demo in Colab, observing a test MAE of 61.77 kilogram and R-square of 90.98 with some insights from the high MAPE and residual plot. Action items. Run the demo network to validate biomass predictions and analyze the residual plot. Second, complete the assignment. Validate biomass predictions against a high-based biomass estimate and report MAE, RMSE, MAPE, and R-square in QA session of Udemy course. Finally, take the quiz to reinforce your understanding. Let's keep advancing your geospatial AI skills.